In this lesson, we will talk about concavity and points of inflection. A curve is concave up when f prime prime of x is greater than 0. In other words, when the second derivative is positive. The graph of y equals f of x is concave up when the second derivative is positive. In other words, when f prime prime x is greater than 0. Notice that the red tangent lines go from a slope of negative to 0 to positive. See, here's a negative slope, then a 0 slope, and then a positive slope. So as we go from left to right, the slopes are increasing. So that's like saying the rate of change is increasing. So if the rate of change is increasing, then the rate of change of the rate of change is positive. In other words, take a look at this. Our slope is negative, 0, positive. The rate of change of the slopes is positive because the slopes are increasing. That means the rate of change of the rate of change is positive. Well, the rate of change is the first derivative. The rate of change of the rate of change is the second derivative. So notice that the red tangent lines go from a slope of negative to 0 to positive. In other words, the slope is increasing, meaning that the rates of change of the rate of change is positive. In other words, the second derivative is greater than 0. When the second derivative is greater than 0, the curve is above the tangent lines. Notice that black curve is above the red tangent lines. When the curve is above the tangent lines, we say that the curve is concave up. Concave down, on the other hand, means f prime prime of x is less than 0. The graph of y equals f of x is concave down when the second derivative is negative. In other words, f prime prime of x is less than 0. So again, notice that the red tangent lines go from a slope of positive to 0 to negative. In other words, the slopes are decreasing. See, the slope went from a positive number to a 0 to a negative number, so the slopes are decreasing, meaning that the rate of change of the rate of change is negative. In other words, f prime prime of x is less than 0. When f prime prime of x is less than 0, the curve is below the tangent lines. So whenever the curve is below the tangent lines, we say the curve is concave down. Now notice, some people sort of cheat by looking at it this way. Concave up, it looks like a U for up. And concave down, it looks like almost like an N shape, an N for down. Okay? So here's the second derivative test. If at a given point f prime of x equals 0 and f prime prime of x is greater than 0, then there's a local minimum. So look at this point right here. The first derivative is 0, but the second derivative is positive because it's concave up. Well, when at this point here, where the first derivative is 0 and the second derivative is positive, we have a local minimum. But at this point, right here, the first derivative is 0. The tangent is horizontal. But the second derivative is less than 0. The curve is concave down. So when we have a 0 first derivative and a second derivative that's negative, we say there's a local maximum. Now, what's a point of inflection? Points at which the second derivative equals 0 are called points of inflection. So these red points are points of inflection. Notice that here, if as I come around this curve to here, everything on the left of that red point, the curve is below the tangent line. So if I was to draw a tangent line in, it would look like this. So to the left of that red point, the curve is below the tangent line. But then as I go to the right of that point, the curve is above the tangent line. So in other words, I went from a region of concave down to a region of concave up. In between, there was a moment where the second derivative was 0. We call that a point of inflection. Similarly, in this example, the curve is above the tangent line. It's a concave up situation. But then, after I move to the right of that red point, that point of inflection, the curve is below the tangent line. So, putting them all together, we have this. This is half of a concave up. This is half of a concave up curve. In this particular curve, the first derivative is positive because it's increasing, but because we're concave up, the second derivative is also positive. So if in a certain interval of a curve, you know that the first derivative and second derivative are positive, you know that the curve has this basic type of shape. Now look at this situation. In this situation, the curve is increasing. The y values are increasing. That means the first derivative is greater than 0. But it's concave down. The second derivative is less than 0. So when you have an interval where the first derivative is greater than 0 and the second derivative is less than 0, we have a concave down situation. Now in this case, we have the first derivative being less than 0, the curve is decreasing, but we have the second derivative being greater than 0. So it's decreasing, but in a concave up way. So if you have an interval with a negative first derivative and positive second derivative, you'll know that the curve has this type of shape. And lastly, what if both first and second derivative are negative? Well, the curve will look like this. It'll be decreasing and concave down. Okay. So what we're going to do now is we're going to sketch a graph of a curve given right here. Well, we know that the first derivative of this curve can be given by 3 times x plus 1 times x minus 3. Now, y prime equaling 0 means that x is equal to negative 1 or x is equal to 3. So we're going to eventually build a number line, an interval testing situation for y prime. And when we do that, we're going to put negative 1 and 3 on that number line for the testing purposes. Now let's look at the second derivative. The second derivative, we've got 6x minus 6. That's 6 times x minus 1. If I let the second derivative equal 0, then x is 1. So what we're going to do is right underneath our interval testing for the first derivative, we're going to make interval testing for the second derivative. And in that interval testing for the second derivative, the only point that we'll include on the interval is x equals 1, the point where the second derivative is equal to 0. Now, we go back to this, this expression right here, 3 times x plus 1 times x minus 3. That is the first derivative. That's the expression for the first derivative. So let's do interval testing right here. Don't look at the second derivative part yet. We're just testing this expression, the interval points being negative 1 and 3. Well, to the left of negative 1, this expression is positive. To the right of negative 1 but left of negative 3, this expression will be negative. And then to the right of positive 3, this expression will be positive. So this is what our number line for y prime looks like. Now let's take our y prime prime. We have our only 0 at x equals 1. To the left of 1, 6 times x minus 1 will be a negative quantity. To the right of 1, 6 times x minus 1 will be a positive quantity. So we'll have a negative followed by a positive. And this is what our intervals look like. And I make sure when I do this interval testing to, I'm almost going to think of it now as one big interval. And I have to make sure my numbers make sense. So negative 1, and then to the right of that is 1, and then to the right of that is 3. So I'm almost thinking of it as one number line. Now, to the left of negative 1, our first derivative is positive and our second derivative is negative. In other words, to the left of negative 1, our curve is increasing and concave down. Then, in between negative 1 and positive 1, we'll have a negative first derivative and a negative second derivative. So we'll be decreasing and concave down. In between an x value of 1 and an x value of 3, our first derivative will be negative and our second derivative will be positive. We'll be decreasing and concave up. And finally, to the right of 3, both first and second derivatives will be positive. We'll be increasing and concave up. And so we see that the general shape of our curve will follow this basic shape in those different intervals. So now what we do is we find the y value at each of those x values. So at x equals -1, that was one of the zeros in our first derivative testing. At x equals -1, we can say y is equal to 15. We plug this back into the original expression for y. So we have to make sure that we're going to put the point -1, 15 on our curve. That's right there. Then we have the point 1, -1, because when we plug a 1 into the expression for y, the y value is -1, so we need to make sure we have the point 1, -1 on our curve, which is right there. And finally, at x equals 3, when we plug a 3 into the expression for y equals -17. So we have to draw a curve that goes through -1, 15, 1, -1, and 3, -17. And we have to make sure that to the right of an x value of -1, our curve is increasing and concave down. And that's what we've done. It's increasing and concave down. This curve is below the tangent line that we would draw at any given point. Now, in between -1 and +1, we know that our curve is decreasing and concave down. So that's what we've drawn, decreasing and concave down. It's decreasing, and the curve is below any tangent line that we would draw for it. See, at this point right here, if I drew the tangent line, it would be above the curve. Now, we get to here. In between 1 and 3, we see that our first derivative is negative and our second derivative is positive. So we'll be decreasing and concave up. We're decreasing and we're concave up. The curve is is above the tangent line. Any tangent line that we draw will be below the curve. And finally, beyond 3, beyond an x value of 3, we have a situation where the first and second derivatives are both positive. So the curve is increasing and concave up. And that's what we have, increasing and concave up. Concave up meaning the curve is above any tangent line that I would draw. And that's what the curve looks like. So now we're being asked in this next question to sketch the graph of the function f of x equals x to the 1/3. Well, f prime of x would be 1/3 x to the -2/3, which is the same as 1/3 times x to the +2/3. In other words, take this factor of x to the -2/3, put it in the denominator, make it positive, make the exponent positive. Now I can think of x to the 2/3 as x to the 1/3 quantity squared. Now, f prime of x never equals 0. F prime of x will be undefined whenever x equals 0. At x equals 0, that denominator will equal 0. So we know that we're going to build number line interval testing, and on the first derivative number line, we're going to have an x value of 0 indicated. Now let's look at our second derivative. If our first derivative is 1/3 x to the -2/3, we bring that -2/3 down, we get -2/9. Subtract 1 from the exponent, we have x to the -5/3. So I can call that -2/9x to the +5/3. Just bring that down, make the exponent positive. And now that's the same as saying x to the exponent 1/3, and then that whole quantity raised to the exponent 5. Okay? So now I see f prime of x never equals 0 because the numerator is -2, but f prime of x will be undefined when x is 0. So I need to make interval testing on my second derivative, where the only point that I'll have to make sure that I indicate is an x value of 0. So notice my first derivative and second derivative interval testing will involve an x value of 0. So this is my first derivative. My x value is 0. If I let x be a negative number, the third root of that will be negative. But then when I square it, it'll be positive. So I'll have 1/3 times a positive quantity. So to the left of 0, the first derivative will be positive. To the right of 0, the first derivative will also be positive, because the third root of a positive is positive. We square it, that's positive. 3 times a positive is positive. So I have 1 over a positive quantity, which is positive. Now let's look at our second derivative. We've got negative 2 over 9 times x to the 1/3 quantity to the 5th. Well, if I let x be less than 0, x to the 1/3 is positive. Raise that to the exponent 5 and it'll be positive. If I let x be to the left of 0, I apologize, I said the first part wrong. X to the 1/3 will be negative. The third root of a negative number is negative. Raise that to the exponent 5 and it's still negative. A negative quantity raised to 5 is still negative. So 9 times a negative will be negative, and negative 2 over that negative will make this positive. But to the right of 0, x to the 1/3 will be positive, raised to the exponent 5 will be positive, times 9 will be positive. Negative 2 divided by that quantity will be negative. So to the left of 0, I've got a positive first derivative and positive second derivative, so I'm increasing in concave up. To the right of 0, I've got a positive first derivative and a negative second derivative, so I'm increasing in concave down. Okay, if you go back to our chart a little while ago, that's what we agreed the shapes would look like. So that's what they look like here. Now, I want to see if y is actually defined when x equals 0. Just because the first and second derivatives are undefined doesn't mean y is undefined. At x equals 0, which is our only important point, our only critical point, y is equal to 0 to the 1/3, and the third root of 0 is 0. So therefore, the point we have to make sure we have is 0, 0. So we put that in. Now, to the left of that, I draw increasing and concave up, like this. And to the right of that, I draw increasing and concave down, like this. Now, every once in a while, I'll see someone try and maybe sketch that curve, bring it back up, or maybe bring this back down. But that would be wrong, because if I do this, that would mean it was decreasing. But I know that it's always increasing to the left of 0. And if I did this, that would mean it was decreasing, but I know that it's always increasing to the left of 0. Similarly, I've seen people do something like this. They maybe take that curve and they draw like this and then they flare it up. That would be wrong, because if I made it increasing like that, that would be concave up, but we know it has to be concave down. So ignore all these black sketches, ignore all of that. The red curve is what that function looks like. Okay, now, in this next example, we're going to figure out all of the intervals of concavity for the function 1 over x squared plus 3. So, oh, I'm sorry, I went out of order. My sincere apologies. Here we go. Now, in this question, what we're going to do is we're going to determine any points of inflection on the graph of f of x equals 1 over x squared plus 3. So let's start with f of x equals x squared plus 3 to the exponent negative 1. Well, what we want to do is to figure out a point of inflection. We want to know where is the second derivative equal to 0. So first things first, we have to figure out the first derivative. Negative 1 in front, raised to the exponent negative 2, times the derivative of what's inside, which is 2x. This negative 1 is in the numerator, so is 2x. This x squared plus 3 is in the denominator if I make it quantity squared. And so I can think of this as negative 2x over x to the 4 plus 6x squared plus 9. I just expanded this out. Now the second derivative will be the denominator times derivative of the numerator minus the numerator times derivative of the denominator over the denominator squared. Well, I can think of the denominator like this, or I can think of the denominator like this. So x squared plus 3 quantity squared, if I square that, I get x squared plus 3 to the 4. Now all we do here is we distribute, and we distribute. And when we do all that distributing, we get this expression. Well, 6x to the 4, this after collecting like terms, we get 6x to the 4 plus 12x squared minus 18 over x squared plus 3 to the exponent 4. We can common factor a 6 out of the numerator, and then we can actually factor this. We have x squared plus 3, and then that's one quantity, and the second quantity is x squared minus 1. So we have 6 times x squared plus 3 times x squared minus 1 over x squared plus 3 quantity to the 4. Well, we can kind of, let's say, cross these out, and we've got 6 times x squared minus 1 over x squared plus 3 quantity cubed. And we don't have to worry about x squared plus 3 quantity cubed equaling 0, because x squared plus 3 will always be a positive number. So what we see is that we've got a second derivative which is equal to this expression. 6 times x minus 1 times x plus 1 over x squared plus 3 quantity cubed. Because if you go back a moment ago, we had 6 times x squared minus 1 in the numerator over x squared plus 3 cubed in the denominator. So we just factored out that numerator. Now, note, as I just mentioned, it's not possible for x squared plus 3 to equal 0, so there are no restrictions. And therefore, we're able to simplify the way we did. Since the denominator can't equal 0, there will be no points to consider where f prime prime of x is undefined. That denominator can't equal 0. So the points of inflection will be at where f prime prime of x equals 0. Okay? Now, f prime prime of x equaling 0 would mean 6 times x minus 1 times x plus 1 is equal to 0, because after we multiply both sides by the denominator, this is what we'll get. And 6 times x minus 1 times x plus 1 equaling 0 would lead to x equaling 1 or negative 1. Well, at x equals negative 1, y would be 1 over x squared plus 3. That was the original equation. And so that would be 1 over 4. So at x equals negative 1, we have the point negative 1, 1/4. And at x equals positive 1, we will have the point positive 1, 1/4. So the 2 points of inflection will be negative 1, 1/4 and positive 1, 1/4. So the only places where you have a point of inflection is where the second derivative is equal to 0. Second derivative being undefined won't give you a point of inflection. Okay? So now, in the next question, it asks us to determine the intervals of concavity for that expression. So we've already done the hard work. The hard work was figuring out where does the second derivative equal to 0, and we figured out that the second derivative equals to 0 at negative 1 and positive 1. Now, a moment ago I said you can't have a point of inflection, there's only points of inflection where f prime prime of x is 0. That's true, but in determining our intervals of concavity, we still do need to consider any x values where the second derivative is undefined. But if you go back a couple of minutes, we established there are no points where the second derivative is undefined. So f prime prime of x is equal to this expression here. 6 times x minus 1 times x plus 1 over x plus 3 quantity squared. The expression's never undefined because the denominator never equals 0. The denominator is positive for all real values of x. So f prime prime of x equals 0 when x is 1 or negative 1. When x is to the left of negative 1, we have 6 times a negative over a positive. When x is in between negative 1 and positive 1, we have 6 times a negative times a positive over a positive, which is negative. And finally, when x is to the right of 1, we have 6 times a positive over a positive. And we have a positive second derivative. And so the intervals of concavity, we can say, we have concave up, in other words, where the second derivative is greater than 0, is where x is less than 1 or x is greater than 1. Or if I want to put it in interval notation, I can say the interval from negative infinity to negative 1 in union with the interval from 1 to infinity. And then if I want to think about concave down, that's in between, so that's in between negative 1 and 1. I can write that in set notation. Or I can put it in interval notation as follows, all the values between negative 1 and 1.